Hi, Mick McQuaid here. This is an impromptu recording occasioned by my poor network connectivity, for which I apologize. I wasn't able to give the remaining parts of my lecture on Sqldf, stringr, and modelr, so I'm going to do them here by recording and ask you to just watch this recording. So I'm starting off with Sqldf. Sqldf is an R package that allows you to run SQL select statements on a data frame. So these are examples of that. And I'm just going to, my computer is not cooperating very well, so I'm going to have to cut and paste each command in. And the first one is just to overcome an issue that I had with Sqldf. You may or may not have this issue. You may or may not need to enter this options g sub fn engine equals R. Now I've already installed Sqldf, and it, as you can see, requires these three other packages, g sub fn proto and R SQLite. I should mention that natively Sqldf uses SQLite 3 as its database engine, but you can connect it to any engine, MySQL, PostgreSQL, SQL Server, Oracle, whatever. And I'm not going to go over the help screen for it. It's a very lengthy, there are a lot of examples, so you should be able to find an example that matches whatever you're trying to do on there. Lots and lots of material on that page. But I'm just going to get right into doing some selects from some data frames. Oh, and this is not found because I haven't loaded ISLR2. So let me load ISLR2. Oh, I don't need to install it. I've already installed it. Let me just load it. You know what? Let me just type this in because I'm having some issues here. So I'm just going to run a few functions here, dim auto, to get the auto dataset's dimensions. So it's 392 rows by 9 columns, and the names of the columns are as follows. And I could inquire of the auto set. I'm not going to do that. I'm just going to get right into Sqldf. So I'm going to say select MPG from auto. And this is going to be the exact same result as saying MPG or print MPG. So it prints all 392 rows. I can do this where cylinders equal 4. And there are 199 cars where cylinders equal 4. I can select 2 columns. Where cylinder equal 5. So there are 3 of these. These are all Mazdas, I believe. These are Vonkel engines. And I can put them into a new data frame called 5sil. And print that data frame. I can select MPG and horsepower from auto where cylinders equal 4, limit 5. So this is only going to return the first 5 such rows. Oops, I accidentally saved that. I didn't mean to do that. I meant to just print them out. For some reason, I'm going to say head auto, so that's just going to give me the first, I think, 6 rows and all the columns. And then I'm going to select just a second here. I'm going to select cylinders equal 4 and horsepower . This is odd. And it looks like there are none. Okay, let's do horsepower greater than 100. And there are 10. Okay, and then I want cylinders in the set 4, 5. And there are 11. I'd like to know the count of cylinders. Well, I'm just going to do a new one here. Sqldf select count cylinders from auto. And there are 392 such instances. I wonder why I would even do that. It seems okay, but a subset might make sense. Select count where cylinders equal 4, so that should return 199. Notice that in SQL, the single equal sign means equals, but I was able to do the double equal sign also. I could do the double equal sign instead, but the single equal sign means equals in SQL, unlike most programming languages where it's an assignment operator. Okay, now I've sort of lost my place here. Where am I? Select average cylinders from auto. So there are an average of 5.4 cylinders. Of course, no car has 5.4 cylinders. I don't even know why I would do that, other than to demonstrate that there are functions that you can use in select statements. Select star from auto. So this is just an equivalent to the head function. So there are lots of examples. If you do $SQLDF, many of the examples show equivalent R commands to SQL commands. Okay, so now I'm going to load the NYC Flights 13 package. So we've already seen this package. It's all the flights. I think there are about 250,000 of them. All the flights departing from LaGuardia, Newark, or JFK Airport in 2013. And it has 5 tables in it. The airlines table, which is just a list of airlines and their 2-digit abbreviations. The planes table, which lists some information about the actual airplanes. So it tells us the manufacturer and the model and so on of each airplane that was used in that time frame. The airports. So these are all the airports, I think, just in the United States. Is that right? I'm not sure if these are just airports in the United States. I know that the flights table, oh, and then here's the weather table. The flights table is just domestic flights in the United States, including Hawaii. And I know that because I've done some queries on it, and the furthest that you get from New York is Hawaii. And the main table in this database is the flights table. So this is what gives us the information about the individual actual flights. And these are not all actual flights. These are all scheduled flights. These are all the flights that were scheduled to depart from these three airlines, from these three airports. But some of them never took off. So consequently, I wonder why it's taking so long to return this. There's nothing wrong with my function. There's just something terribly wrong with this computer. It's needs to be taken out in a field and shot. And I've had a new computer on order for seemingly forever, but that hasn't arrived. Okay, so we see that the flights, it seems I've done it okay, well, in any event, it is a tibble of about 250,000 rows. The head of this is just 6 rows, of course, and 19 variables. So you see the first few variables here, including the departure time. So the departure time is NA for flights that were scheduled but didn't actually occur. We have the year, month, and day of the flight. So these are all in 2000. Year is always 2013, and they're in order from January 1st through the end of December. The departure delay, the arrival time, the scheduled arrival time. So this is the actual arrival time and the scheduled arrival time. And then there are 11 more variables: the arrival delay, the carrier, the flight, the tail number of the airplane. That's a unique identifier for each airplane. The origin, this is always either EWR, JFK, or LGA. The destination, this can be any place in the United States. The air time, the distance that was flown, and hour, minute, and time hour are the number of hours that were flown, the number of minutes that were flown, and the time in hours and minutes that were flown, I think. Or the time in, I can't remember what this is. But it's a date time data type. Okay, so now we're going to do a join. So this is the actual purpose of SQLDL. You probably wouldn't do it just for the things that we saw up here, because there are equivalents that are, in most cases, just as easy or easier. But for joins, this may be easier. Oops. Is that right? Okay, so this is not right. What have I done wrong here? I can't see the error here. Okay, so now you get to see me try to debug what I've done. So name from okay, so that gives me the name of an airport. There are 1,400. This doesn't make any sense at all. Penn Station is not an airport. This could go on for a while. So this is selecting all the unique temperatures. There were 26,000 different temperatures. I can't imagine why you would ever want to know that, but I wanted to was that my syntax error? Oh, that was my syntax error. I didn't have from in there. Somehow I didn't say select name temp from airports, join weather on origin FAA. So these are all the different temperatures that were recorded for LaGuardia, for example. This doesn't seem like a very useful query, but it does join two tables, and it does demonstrate trying to debug a query. So when you try to debug a query, I think that the important thing is to try different things. And if you try different things, that may give you some idea of what to do, what to try. Let's just do this dim weather. For some reason, I wanted to know that. Oh, okay, so there are 26,000 temperatures. So actually, there are quite a lot of duplicates here. What if I say select distinct? There are only 412 distinct ones. And that's for all three of the local airports. So this origin equals FAA is the three-letter airport code. So we're joining on origin equals FAA. I think if we try to join, let's see, let's select well, let's see. I can't remember all the column names. Let's do head flights. So let's. I want to join on tail num with planes. What would be a good carrier? Let's do carrier and model. Well, let's do carrier and manufacturer. So let's say select distinct carrier manufacturer from flights. And this inner join wasn't necessary. The default is inner join. Join planes on, and I think I can just say tail num. I don't think I have to say tail num equals tail num. Let's try this anyway. So it's unbelievably slow, but that slowness may be because of my computer. It may not be that. I mean, SQL, tuned SQL is as fast as you can get. Tuned SQL on a live database is as fast as you can get. So I do need to say tail num equals tail num, I guess. Is that going to do it? And again, notice that in SQL, I'm able to use the single. That's weird. Flights has tail num. Tail num is a string in both cases. That one is a mystery to me. I really can't say why that is. Okay, so I'll research that, why I would get that name there. I'll do that offline. I want to go on to the other parts of this lecture, which are strings and regular expressions on the one hand and model basics on the other hand. So let's talk about, let's do a little bit of stuff with strings and regular expressions. Okay, so strings and regular expressions are one chapter, and there's a package called stringr, which we're going to use. So I'm loading the tidyverse and loading stringr. I think since this was published, stringr may have become part of the tidyverse. I'm not really sure about that. But in any event, here are some examples of strings. So they're in R, they're called character vectors. And you can see that we can use quote marks or apostrophes to delimit a string. And we can escape both quote marks and apostrophes. So PQRS shows all different possible examples. We can see the raw string by saying write lines and then the name of the string. By placing these strings in parentheses, I've caused them to be printed out at the same time that they're saved in the associated objects. And if I want to get help on character quoting, I need to say question mark, apostrophe, quotation mark, apostrophe. Yuck. Okay, I can do a bunch of string functions, 39 of them, and they all start with str underscore. And one is the length. What is the length of a string? So the length of the string A is 1, of course. The length of the string R for data science is 18, and the length of the string NA is NA. I can combine strings. So X, Y, and Z is combined into one string X, Y, and Z, X, Y, Z. I can also use a separator character when I combine them. And actually the separator is a string. I shouldn't have said separator character. I can use a separator string, so that can be a single character or a collection of characters. And I can combine strings with vectors of strings and get multiple strings. But I have to explicitly request NA to be included if it is desired, or it will be silently passed over. So you can see that in this case, I've said replace NAs that are how does this work? Combine, concatenate A, B, C, and NA with the dash and the pipe character. Okay, so in this case, it didn't explicitly do the pipe character and the dash with NA. In this case, it explicitly does do that, and that is because of the string replace NA function. Vectors of strings differ a little from strings, so here are some strings. Here are some vectors, each vector being a string. And I can collapse a vector of strings into a string. The collapse option converts to a single string. Objects with length 0 are silently passed over. So for example, in this case, false has caused this to be length 0. So this says, good morning, Hadley, because the time of day is, wait a minute, good time of day, name, if birthday. So this being false makes this be of length 0. I can extract a part of a string with str sub. So I can take, for example, character 1 through character 3. If I take character -3 -1, I get the last 3 characters, the third from the end to 1 from the end. And again, R is, as usual, counting from 1 instead of counting from 0, like most programming languages. I can assign a value with str sub, so I can say str sub x1 1. So I'm assigning to the first character of this, I'm assigning lowercase string sub x11 gets so this just changes to lowercase. Were these uppercase? Oh, these were uppercase. Okay, I see. So this is changing the first character to lowercase, and we're doing that for the first character of X, of the string X. We talked briefly about locales before, so every computer, at least on Linux and Mac, and I believe on Windows as well, has a concept of a locale that it's in. So my locale, for example, is EN_US, which means the English language in the US. So all the conventions that are common to the English language in the US are obeyed by programs on my computer that recognize locale. So R is such an example of such a program. So if I say that the locale is Turkey, I get two different I's, with and without a dot, and it has a different rule for capitalizing them. So str to upper will just return I for the case of I and dotless I if I don't give the locale. In other words, the locale is implied to be my locale. So the locale implied here is EN_US. And the locale here is not implied, it is explicitly TR for Turkey. So consequently, the capital I with a dot gets a dot, and the dotless capital I gets a capital I without a dot. Okay, so there's a section on regular expression that uses str_view, and this only works in HTML. So you can do this through the graphical installer or by saying this, and then strview will show its output in the default browser, and the default browser for Rstudio is an internal browser. The default for when I run this on the command line, it's just whatever is my default browser, which happens to be Firefox. So it opens, so on my machine, this all opens a window in Firefox. And the reason for this is that it wants to be able to highlight some characters. And there's no, in the terminal, there's no way to highlight characters. Well, there is. I mean, I could use an underscore, and in fact, that's what I'm going to do for the rest of this. The rest of this slideshow, because it looks bad to do screenshots. So this is a screenshot of the browser, and screenshots don't look that great. They're pixelated. And so this is the output for string view, but I'm going to simulate that in the following ones by just using an underscore. So I'm using an underscore the way that string view would use this frame around the characters. So if X is a vector of these strings, and I only want to look at the regular expression AN, this is the result. So this is a regular expression because literal strings are valid regular expressions, but regular expressions are much more extensive. So for example, in regular expressions, dot resolves to any character. So this regular expression here resolves to any character followed by A followed by any character. Now you see that that doesn't work in Apple because there's no character before the A, but it does work for banana and pear because there is a character before the A. Now you might wonder how it decided to do BAN instead of NAN. So NAN would also be a valid match for this regular expression. And in general, regular expressions are of two types. They're either lazy or greedy. And a lazy regular expression matches the first thing that it comes to that is a match. A greedy regular expression tries to match everything that it can. And in both of these cases, this would be a lazy regular expression that would just go to the first one. I can repeat the expression to make it add to the last one, and regular expressions don't overlap. So if I give this regular expression and get this output, I won't get NaN because NaN would overlap the first instance of the regular expression being matched. Okay, so the dot matches any character ordinarily. If I put a dot in, it matches any character. So what happens if I want to actually match a dot? So here's an example where I have a dot in the string and I would like to match that. So in this particular string, I would have to put a backslash to escape the dot, but then I also have to put in another backslash to escape the backslash, because backslash is a special character. So I have to use a double backslash to represent an explicit dot. And this kind of gyration is really common in regular expressions and makes regular expressions look ugly and complicated. There are plenty of special characters in regular expressions. So for example, I have this character of the circumflex, or the caret, marks the beginning of an expression. It also has other functions. Inside square brackets, it means negation. But outside of square brackets, it means the beginning of the string. So this will only match an A at the beginning of a string. And of course, the only A that's at the beginning of the string is this one. $sign matches the end of the string. So this will only match an A at the end of a string. So it only matches this one. I could say, for example, caret A $sign, and I would get nothing because there's no case where we have caret, where we have the first letter and the last letter is A. A string that is just the single letter A. I'm going out of frame here, I see. Okay, so now I can use both to match only a complete string. So for example, I can match here apple occurring as the entire string. So this is a complete string from the beginning to the end of the string is the word apple. And of these three, only one of them matches that. I can put all of these things inside a regular expression. So if I put \d, that matches any digit. If I put \s, that matches any white space. And white space is defined as a space, a tab, or a new line. This is the alternating operator, or the alternation operator. And this matches any of the characters inside the square brackets. Here's where I mentioned the negation. So this matches the negation of A, B, and C, that is anything except what's in the square brackets. And this has to be at the beginning. If I put this caret at the end of here, it would simply represent an actual caret. It has to be, the only place that it represents negation is at the beginning of an alternation operator. And the pipe operator means or, and I often have to put parentheses to signify what exactly I'm using in the or expression. And A and B are strings, so I can use this for substrings. So here are some examples of these. So here I've explicitly said I want to match E or A. So this matches gray spelled with an E or gray spelled with an A. I can do repetitions of characters. So I could, for example, say dot question mark. That means any character, or nothing, no character at all. I could say dot plus, and that would mean one or more. I could say, for example, any letter followed by a plus. I can also say any given letter followed by a question mark. 0 or more, which is a really frequent one to use, 0 or more characters. exactly n characters. So n here has to be a number, n or more, and these are placed after a character that you want to have exactly that many of, or n or more of, or m again is a number, at most n. So I can say between n and m occurrences of that character or string. So here's an example of this. I say I want anything that's CC followed by 0 or 1 examples of CC, of C, right? 0 or 1 of whatever preceded it. So what preceded it was a C. So this is any two C's followed by another C or followed by nothing. And this is a lazy operator, so it goes to the very first pair of C's. This is CC followed by, let's see, 1 or more C's. So this C has to include the C in its match. In other words, this one didn't, because this is CC followed by 0 C's, and that's fine for a lazy operator. But the only thing that matches CC plus would be 3 CC's. It has to be at least 3 CC's. It could be more. C followed by L or X plus. So this is C followed by L or X plus is going to match any series of X's or L's after the L or X. C2 will match exactly 2 C's. So we have exactly 2 C's here. C2 comma will match at least 2 C's, but it could match more. So it can match 3. Oops. Here is, it has to be between 2 and 3. And here it has to be between 2 and 3, but it can be 0 of these 2 or 3. See, we've put 2 different operators here. So all of this stuff in curly braces is one operator. The question mark is another operator. So the question mark rules in this case and gives us only 2 C's. Parentheses define groups that you can refer to as group 1 or group 2. So the very first set of parentheses is group 1. So group 1 is any 2 characters, and this is followed by group 1, and we have to put the double backslash to escape the backslash here. So this is any 2 characters followed by those same 2 characters. So these are all the cases where we have 2 characters followed by those same 2 characters. So here are different things that you can do with a regular expression, and really by far the most common is this fourth one, replace matches with new values. So this is a better version of find and replace, because you can find patterns and replace them with patterns without knowing the actual details of what the pattern matches. But you can find out which strings match a pattern and count them. You can find where in a string of position, where in a string there's a match. You can extract the contents of matches and use them for something else. And this most common one, replace matches with new values, find and replace operation, or split a string based on a match. So here's detecting matches. So string detect detects any place that has an E, any string that has an E in it somewhere. And so it returns a Boolean value. And we can do something with that Boolean value. We can use this as an index to those strings. And then if we use it as an index to those strings, it'll actually return these strings instead of true and false values. True is stored as a 1 and false is stored as a 0, so we can count in the words vector, we can count the number of words that start with the letter T, and we can take the sum of that, and the sum of that is 65. There are 65 common words that start with T. What proportion of common words end with a vowel? So these are all the vowels except for Y, which is only sometimes, actually Y is, I guess Y is not always a vowel at the end of a word. So anyway, these are the letters that always function as values. So any of these followed by the end of the string. So 27% of them, and this is the mean, this is the average of those. So 27% of the words contain a vowel as the last letter. Find all the vowels, find all the words with one vowel and negate it. So these are all the words that contain a vowel, and then we say the negation of this. Or we could find all the words consisting only of consonants. So this is a word that starts with the negation of a vowel, followed by at least one such character, followed by the end. So this is going to be all consonants up until the end. And then we check to see if these two are identical, and indeed, they do return the same result. And you should always check your work with regular expressions because it's very easy to get confused with regular expressions. So which of the examples is easier to understand? This fails. This gives the short list of common words without A, E, I, O, U, but this one does not work. Why is that? So this is the subset of words that contain A, E, I, O, U, and we negate that, and what have we got left over? Actually, that's an interesting question. You should run that and find out. String subset is a wrapper around logical subsetting. So string detect within the common words vector, words that have X at the end, and there are only 4 of these, 4 such words. String subset actually will return this. This would return by itself, just the part inside the index would return all trues for these 4 words and falses for the other 900 words, or however many words there are. I think there are 900 words in that vector. If strings are in a tibble, you have to use filter. So I filter P and get these words. So this is a tibble that consists of words plus a letter that indicates its index number. So box is the 108th word, sex is the 747th word, 6 is the 772nd word. String count will tell us the number of matches per string. So there's 1A in apple, there are 3 A's in banana, 1A in pear. On average, how many vowels are there per word? So the number of words and vowels, there are an average of almost 2 vowels per word in the common words, collection. We can use string count with mutate. So I'm going to get all the vowels, the number of vowels in words, and then the number of consonants in words, and create new columns on that basis. So this is a new, so I could assign this, let's say I say Q gets mutate and then all of this stuff, and Q would be a tibble with 980 rows. I mentioned before that matches never overlap. So if we do this, ABA, this has been used up now, and we can only look at this. So then we find ABA in this. We have two cases of ABA in here, even though it looks like we have three, because matches never overlap. There's an example of sentences. There are 720 sentences called the Harvard sentences, for a bunch of examples here. And the sentences here are the first 6 sentences. Okay, they're just, you know, relatively simple sentences. This one obviously is an imperative. This one has a subject and predicate. I mean, this one starts off with the predicate. So we can make a regular expression from a list of colors. So we have these colors, and we can say, we can collapse these into an OR set. So color match is now going to be any of these colors. So we can use that in the and we can do it with full words. So \B means a full word, boundary. B stands for boundary here. So colors preceded and followed by a word boundary are the color words. So notice that these are the colors. So it's any of the colors preceded by a word boundary. And a word boundary can be a period, a comma, a space, or other punctuation. And we're going to collapse this into an OR bar. So this is going to be any of the words, like in an either or kind of construct. So we can then say which sentences have these color words, and we can extract the colors from this group of sentences. So this is a group of sentences. And these are the color words, and we're extracting those. So we know that the first matches are, the first sentences have blue. And if we go back, well, no, actually we can't go. We don't have an example of this. But these are the first, the color words in the first 3 sentences that have color words. We can select sentences where the color words count string count of color words is greater than 1. So we get these sentences. So these are the only sentences with multiple color words. We can find words that follow the articles a and the. So this is either a or the, followed by a space, followed by 1 or more spaces. Oh no, followed by not a space. I'm sorry, this is the negation character. So this is a space, and this is not a space. So this would be, so this is the word as anything that doesn't have spaces in it. And so we put that into has art plus. We start out with sentences. We get the subset of art plus, and then we take the head of that. So the head of that is what goes into art plus. So this is only 10 sets of these kind of constructs. Okay, and then we extract the art plus. We extract this type of string from the resulting set, and we get these 10 results. And why would it be A helps? That doesn't make any sense to me at all. What could possibly be the source of that? Well, we could look inside. I'm not going to open it now, but we could look inside and see where this is. All the other ones make sense to me, except A helps. Use string replace. So this is the most common usage. And this is a cooked example, replacing the vowels with dashes. And notice it replaces only the first occurrence. So I would have to add a global option to this to make it replace all of the ones. And I could instead just use the str replace all function to replace all of them. So I have oh, okay. So I have this vector of 1 house, 2 cars, and 3 people. So it's a vector of character vectors. And I want to replace every occurrence of 1, of the numeral 1 with the word 1, every occurrence of the numeral 2 with the word 2, every occurrence of the numeral 3 with the word 3. So the output of this is going to be 1 house, 2 cars, 3 people. Here's a cooked example for back references. So we're going to replace the strings, and remember this is a word. So this is not a space followed by 1 or more not a spaces, followed by a space, followed by a word, followed by a space, followed by a word. So we're taking the first 3 words and we're substituting for those. The first word is going to still be the first word, but second we're going to have the third word, and third we're going to have the second word. So we're swapping the location of the second and third word. So instead of the birch canoe, we're saying the canoe birch, without knowing what the word is that we're actually replacing. So this is a cooked example, but it's an example of why regular expressions are powerful, because you can replace things that you don't know what they are by using patterns. So these are all, silly examples, but this principle is very important. We can split a string. Oh, this is actually pretty common too, splitting a string into pieces. So we often want to do things like counting the occurrences of words in sentences. So we want to split the sentence into its words and then count up the number of times, for example, that the word the appeared. So that's a very typical linguistics task. And if we simplify this, we get a matrix. And some of the cells are empty because not all cells are the same length. So the matrix is going to have as many columns as there are words in the longest sentence. But we could have a particular number of pieces. So we could, for example, say we only want 2 pieces here. So we're going to split off the first word, we're going to simplify that, and we're going to just look at 2 pieces. So the first word is 1 piece, and then all the other words are the second piece. So we have a matrix, in this case, that's 2 by 2, because we're only extracting the first 2 rows with the head function. So there are 2 rows and 2 columns. Okay, so that's just some of the high points of this chapter. There is a lot of detail in this chapter, and a data analyst should be comfortable with using regular expressions, although regular expressions are deprecated for production tasks. So I suggest that you not use regular expressions in production code, but in prototype code, regular expressions are quite valuable. And using regular expressions is very common. In fact, there are a lot of people who just use Python because they like its regular expression syntax. I personally use what's called PCRE, which is Perl compatible regular expressions in both Vim and Perl. R is more known for its graphics and large selection of data analysis packages, but knowing how to use regular expressions during data analysis can shortcut many tasks. So it is still useful to be able to do regular expressions in R. But in general, whether you do your regular expressions in R or in one of these other tools, and there are plenty of such tools. There's the grep command, the awk, domain-specific language, and lots of tools that use regular expressions. You should know how to manipulate them for small tasks and one-off tasks, but probably not for production tasks. Okay, so that's the end of that slideshow, and I have one more slideshow to do, which is this one, model basics. So this is the most complicated one. And let me just see what my time frame is here. I have, I may not be able to get through all of this one. So I'll do as much of this as I can. I have another meeting coming up. So it took me a long time to set this up. So I'll get started on this anyway, model basics. And this is a dense slideshow. So this is something that we're not going to pursue a lot in this course. Getting a low-dimensional summary of data and partitioning data into patterns and residuals. So this is essentially the mission of regression. So we have potentially a family of models that have this format, y equals a1 plus a2 times x. You're going to more typically see this as beta 1 plus beta 2x. Fitted models, which have a number in place of this parameter. And the fitted model is usually the best model from some family of models according to some criteria. So we generally use the least squares criteria, and the best model that we can come up with may not be useful, so we have to evaluate the model. And a model is always a reduction of the truth into simpler terms. So a model never represents the truth. In fact, there's a famous example of a Borges short story where he had a map that was the same size as the land that the map guided you to. And so, of course, and the map was eventually became unreadable in that story. Okay, so the prerequisites are the tidyverse, the modelr package, which is not part of the tidyverse, and we're getting rid of warnings in this case. So we're going to start off with a simulated data set. So this is 30 dots that is in the modelr package as the data set called sim1, and it has an x and a y value, and we're just doing a scatter plot of it. And you can see that it's, you know, a linear model would fit this data pretty well. So we're going to create a bunch of models randomly. So the model consists of the coefficients for the intercept and the slope. A linear model, that's the definition of a linear model, is just those two numbers, a1 and a2, a1 being the intercept and a2 being the slope. So we can randomly generate a bunch of models. So these are uniformly distributed. There are 250 of them, and the intercept ranges from -20 to 40, and so that's going to range outside of the data range, but it's certainly going to enclose all of the data range. And then did I say slope? I meant the intercept. Then the slope is anything from -5 to 5. So the slope could be this steep. or negatively that steep. 5 to 1 to minus 5 to 1. We have easily 5 here, right? No, 4 here. Okay, so this steep or minus that steep. And we can plot these models on the data. So we can say an AB line can take an intercept and a slope, and we use A1 as the intercept and A2 as the slope. And we make these not completely opaque, so we can see through them to each other. And we also are, and we're using these 250 examples of A1 and A2, and GOnPoint is going to inherit sim1. So GOnPoint is going to show us the dots for sim1. So this is the result. We get the dots for sim1, and we get all these models ranging from a slope of 5 to minus 5. So it's a mess. We have all these models, and most of these models are completely irrelevant to the data. And what we would like to do is find the model with the smallest error lines, and there is a technique that is widely accepted for doing that, which is called least squares. But we're going to use a more haphazard technique to get a bit of an understanding of how we might get to least squares. Okay, so we want to minimize the sum of these lines, the sum of squared error, the squares of these lines. We do the squares so that these aren't negative. So this is a positive number. This is a negative number. Okay, if we're measuring from the line. So we want all positive numbers to get the sum of all the numbers. So we do instead the sum of squared numbers. We could do the sum of absolute values of numbers, but absolute value function has a kink in it at 0. Absolute value function is V-shaped at 0, and the squared function is U-shaped at 0. And so consequently, we can write a mathematical proof about the squared function, and we cannot write a mathematical proof about the absolute value function because of that kink. So many of the tricks that we use to write a mathematical proof require that the function that we're doing the proof about be everywhere differentiable. And a smooth curve like a U is everywhere differentiable, whereas a kinked curve like a V is not everywhere differentiable. So that's why we use this sum of squared error instead of sum of absolute value of error. We can prove that the one is optimal. Okay, so step 1 is a function that takes parameters and data as input and gives predicted values as output. So our function is going to take in a vector of a vector of A1 and A2, and the data, which can be the data from sim1. Sim1 is this input and output, the input being x. So we're going to take the x value from sim1 and an intercept and a slope, and we're going to output for each of the 30 cases in sim1, we're going to output a prediction. So this is a prediction of sim1's y value. This is not sim1's actual y value. Then we're going to collapse those 30 outputs into one number, so we're going to find the root mean squared deviation. So we're going to take the square root of the square of the differences and average them and take the square root of that. So this is going to give us this distance measure. And then we're going to use this function, this measure distance function, inside of another function. And this function is going to take the two inputs of intercept and slope, and the data, and give us an output, which is this the distance. Then we're going to take the model, so we have 250 of these. We're going to take these and we're going to use per. This is another package, and we're going to map map to double. What is map to double? Map to double is a function, I guess, in per for mapping these two inputs into this function. And the result is going to be 250 models with a score for how well each one performed. So this is the dist measure that we got from here. The dist measure that we got from here using these two as input. So this is a great distance. This is a small distance. And what we want is the smallest distance. So we're going to take the smallest distance models, that is the ones that have a rank of less than or equal to 10. We're going to take those models and plot them against the Sim1 data. And here's the output. So these are the 10 best models. So we randomly came up with 250 models, and then we measured them to see how good they were according to some criteria. And the criteria was the distance, was the total distance. And the lightest lines here represent the smallest distances. So this is probably the best one. This is the second best one. This is the third best one, and so on. Another way that we can compare these models is to do a scatter plot of the intercept and slope. So this is quite a different way of measuring these. And we take the 10 with the smallest distances and just highlight them in red. So this is two sets of points. This is all of the points, and this is the points with the rank of distance 10 or less. Okay, and we made them larger than the standard size and colored them red. And then we colored these over we placed these over them, so that actually places the small dot, standard size dot, over the large red dot. So we have 10 dots here, and you see that they're in a region, and there is kind of a boundary to that region along the x-axis and a boundary to that region along the y-axis. So random search identified a neighborhood that was a good neighborhood. That is the boundary along the x-axis and the boundary along the y-axis. And we can plot the results just in that neighborhood. So here are the results in that neighborhood. Again, the 10 best in that neighborhood. But this is a smaller neighborhood than what we had before. So we can take the original data, which is here, and overlay these 10 best on it. And you see that they're much better than the 10 best that we got before with the random search. And we could make this grid finer and finer as we search. Or we could use a well-known optimization method. And so there's an optim function that optimizes and will give the best A1 and A2 to fit Sim1. So if we plug measure distance into this Sim1 data, the best parameters will turn out to be 4.2 and 2.0. And then we plot those with the intercept being this number here, and this number here being the slope. And this is what we get. And this is using Newton's method. Wickham 2017 calls it the Newton-Raphson method, but it's more typically called just Newton's method, and it is the most famous, the first kind of popular optimization method. It's a crude method. It has a lot of faults, but it's very often used, and it was used, for example, in my computer science education. That was one of the first things that we had to implement was Newton's method, which uses the derivative of a function to find the next point along a search. A better method is the LM method. So this is the common, when you take ISTE780, this is the common method for regression that you will use. So here we simply take the y values from sim1 and the x values from sim1, and we come up with this. This method is provably optimal and very fast. Now we need a more general method than what we've just seen because we need it to work for both the predictions and residuals. And by residuals, we mean the, recall those little blue vertical lines that I said were the errors. Those are also called the residuals. Those are what's left over when you've created the model. Those are the things that you couldn't explain, those little blue lines. Those are residuals. And if we have a good model, the residuals have no pattern at all. The residuals are kind of random and fulfill some assumptions. So we can generate a grid over the data space and add predictions to the data frame. So the PRED column is the predictions. And we can plot the predictions in the data. So the data is just the geom point. The geom line are the predictions. And this gives us the same prediction line, 4 point something and 2 point something. Was it 4? Yeah, 4 and 2. And now we add the residuals, the differences between what we've predicted and what we've actually seen. And so we plot those to see the spread of the residuals. And usually what we do is scatter plot the residuals. So here are the original observations, and here are the residuals. And what we want to see is no pattern here. So if we could predict, if we could go up from here and then predict this, that would be a pattern. So typically the patterns that we see are either linear, like the original data. If we see a linear pattern, we know we have a bad model. If we see a negative linear pattern, we have a bad model. If we have a curvilinear pattern, we know we have a bad model. And that's the most common thing to see because a linear model can't capture a nonlinear reality. So if we see a curve, we're instead going to see a curve here. If we have a curve in the original data, we're going to have some type of a curve here. And I'm sort of trying to draw U's and humps here to indicate those curves. So that's what we don't want to see. If we see that, we know we have a bad model. We need a better model. Now, the mechanics of how the pattern is discovered by R involve this model matrix. So we create this formula here, y explained by x. This tilde means explained by y explained by x is converted into this by R. And model matrix is this in terms that R uses. So we can get the model matrix for this data frame, and this is the model matrix. Okay, given this data frame where we're trying to explain y by x1. And we can drop the intercept column. We can say -1. And we can add more variables. We can add x2 to the model to see how the matrix grows. But there's a potential problem. Oh, yeah, categorical variables are handled differently. So the categorical variables are turned into zeros and ones. So this is sex male. It's turned into 1 for the male sex and 0 for the female sex. So here's a simulated data set with a categorical variable where the categorical variable is A, B, C, or D. We can fit a model and generate predictions. And the predictions are the mean for each category in a categorical variable. We can overlay the predictions on the original data. So here's the original data, and here are the predictions. And so these predictions are, again, just the mean for each category. Sim3 is a data set in the modelr package that contains a categorical predictor and a continuous predictor. So there's x1 is a categorical predictor, and x2, oh no, I'm sorry, x2 is the categorical predictor, x1 is the continuous predictor. And we can fit two different models to this data. We can either add x1 and x2, or we can multiply x1 by x2. And there are functions to support visualizing these. We can do a data grid and gather predictions, and we get as an output a grid, a tibble of all the possible combinations. And we can visualize the results with one facet per model. So there are two models here, the additive model and the interaction model. The additive model and the multiplicative model differ here because the additive model has the same slope for each line, whereas the multiplicative model has potentially, not always, but potentially, and in this case definitely, has a different slope for each line. That indicates that there is an interaction between these variables. And so you can guess which model is better. I would, of course, guess that the interaction model is better because there is an interaction in this data. But we can plot the residuals to find out. And what we see is that the first model has a pattern, a clear linear pattern, a clear curvilinear pattern, and not so clear patterns. So there's less patterning in model 2 for the different values of B and D in particular. We can do the exact same thing with dataset Sim4, which has two continuous variables. So we're doing exactly the same thing here and getting a similar grid, except that these grids are more variable. And we can visualize these as 3D surfaces according to model. So these 3D surfaces have like a density. You could imagine that you're looking down at a landscape, and that the lower part of the landscape, say the landscape near the beach, is here, and the landscape in the mountains is over here. And they look alike in this viewpoint. But if we look at a sideways view, if we look at them sideways, we see that there is interaction in Model 2, but not in Model 1. Model 1 has parallel lines. Model 2 having no parallel lines indicates that there is interaction between x1 and x2. We can look at the other sideways view. So there's, if you imagine the 3D space converted into two sideways views, we can look at it the other way and see that there is interaction here as well. And as before, you have to look at the residuals. You can check out the data set because it is in Model R. And if you took another course from me, that's ISTE780. In Rochester, it's usually called KDD for knowledge-based data discovery. You know some other techniques for evaluating residuals, so you'll learn those in ISTE780. some of the things that you can do include transformations. So as long as you have a lossless transformation, that is a transformation that's invertible to the original data set, you can do things like straightening out curves and unpacking packed observations and other stuff as well. But anytime you use these symbols, you have to wrap them in the I function. And if you forget to use the I function, weird things can happen. And you can find out what weird things are happening by using model matrix. So here's the data. And in this model matrix, we don't see the x squared term. We just see the x term because we failed to wrap this in an I function. It has this special character. So if we do it correctly, now we get the squared function, x squared, in the model matrix. We can also use another kind of function called a natural spline to approximate weird curves. So complicated functions, and I think I have an example of a nonlinear function here. So this function is a sine function. So I'm multiplying, and I'm using pi, so I'm using the typical sine curve that varies according to pi. And then I'm going to plot this along with the sequence of 50 points from 0 to 3.5 times pi for x, and then I'm going to do a random normally distributed, this is random normally distributed noise along a sine function. So this is going to have the characteristic sine curve that looks like that. And it's just going from, I guess, from 0 to 10. Okay, so this is a sine wave with some normally distributed error to it. And I can fit models to this data set with increasing degrees of freedom. So so this is a natural spline, and this is 1 degree of freedom, 2 degrees of freedom, and I think I have a plot of it here. So here's the model with 1 degree of freedom, a model with 2 degrees of freedom, model with 3 degrees of freedom, and you see that the more degrees of freedom, the more the natural spline fits the data. So the 5th degree of freedom is the best. Okay, and that's it for this Model R lecture. You should read this chapter. This is the hardest chapter in the, I think this is chapter 12 in the print version of the book. And it is the hardest chapter by far of the book. It gets the most of a preview of the next course that we'll see in this course, the most preview of 780 that we'll see in this course, where we're trying to simplify our view of data to create a model of the data that can actually be used to make inferences about the data. You know, like what would the next point be in the data set that we haven't seen yet? Okay, so thank you for your attention. I'm going to end the recording here, and look forward to seeing you next time. We're going to try it in person, I mean not in person, but by Zoom next time. And then if I run into the same problem of frequent drops in the network connection, I will revert to this kind of recording again. But feel free to email me with your questions, and feel free, if you want, to use the email function in my courses to email the whole group with your questions, and then I'll answer to the whole group.